Hello. Okay. So, welcome to this session. Um, I want to believe that you can hear me more clearly on your side. And welcome. I hope you can hear me well on your side. I would like us to talk about cloud and edge computing for distributed machine learning. And when looking at this, you have built some models. Then the question comes, are you able to deploy them, or how are you handling them in terms of training? The other thing that you'll need to know is you'll need to do some lab on how to load this data, deploy on the pipelines that still runs fully on Google Colab, while also demonstrating the real cloud edge machine learning architecture. So we are going to load some data using Spark distributed processing. We shall as well as train a model, and then we shall convert it to edge format and then deploy it with some TensorFlow Lite. Then after that, we shall be able to simulate the inferences on this Raspberry Pi and mobile edge devices so that it can be able to work with any device that's available. So that is the lab prac that I've designed for you today, and you'll be able to implement that at the end of the day. So the key things here is that what is the cloud edge computing on distributed machine learning, and how is it important to you as we handle machine learning platform or development of machine learning and these distributed machine learning systems. As I told you that machine learning is a very important aspect because you can't talk about AI without talking about machine learning. Because machine learning is a subset of AI that now handles with models and data, and it's very, very crucial and very important that you should be able to master its importance on that. Uh, is there a chart somebody has made, or what is it? If I can see. Can't see your chart. Mouse can't get your charts there. Don't know. If somebody has sent a chart, I'm not able to retrieve that chart. But I hope my voice is very clear on your side, so that we can be able to move with speed. Okay. Thank you for that response. And then I hope I've shared my screen too. That's okay. So the key thing here is to note about we say that you can develop models, then you can deploy this using using what is called fast APIs. You can now use that to be able to access it within the other system. So mostly you can deploy your model separately, and then you can use the fast APIs to be able to link with AI APIs to be able to utilize the data that you have trained. Sometimes you can as well as deploy it or link it directly with the you can easily link it to or deploy link it with any deployment sector to be able now to connect with any other device that you want to consume that model. Now for that case, then we need to be able to know how have you trained your model, how do you expect it to operate, is there any additionals that you wish to use it for, uh, how do you deploy it, is it in Google Space, AWS, that's Amazon Web Sockets, web services, or where. So all these are very, very important things that you need to note. So for us to have this beginning, I'll just to have a very brief introduction about that, so that you can be able to understand what is cloud and edge computing for distributed machine learning. I'll begin by telling you that cloud and edge computing is an architecture where data processing and machine learning tasks are distributed between decentralized cloud servers and decentralized edge devices. I think I don't know if I have done, I wanted to do some captioning here so that the system can easily work with it. I think I have some difficulties with my system. One of the things here are disabled. Ah, but you can hear me, that's okay. Even if I don't enable the captions, you can be able to hear me well. I've said that cloud and edge computing is computing architecture where the data uh, where the data processing and machine learning tasks are distributed between centralized cloud servers and decentralized edge devices. So what do we have when handling this? We have to handle some two things. One of them is the cloud computing. And when talking about the cloud computing, we are saying it uses powerful remote data centers to store data, train machines, learning models and also perform large scale processing. And in that case, then we have the other component that we are looking at, which is called the edge computing. And when dealing with edge computing, we are just talking about it moves the computation closer to where the data is generated. For example, most of the data come from different sources. And these sources, I'm very sure that you understand the sources or the areas such as mobile phones. We have mobile phones uh, that we normally use. We also have sensors that sometimes are used to collect real-time data, satellite mapping that are also used to generate some large volumes of data, especially when you don't want to the person who is collecting data to be directly on your system, but it should be on the ground collecting some information, GPRSs, and so on. Then we have things like IoT devices, the cameras, the edge servers. All these are edge computing. That means that moving computation closer to where the data is generated. So all these devices are used to generate data. Now, in distributed machine learning, the training or inferencing of these models is mostly shared rather than on a single computer. So it's mostly shared across multiple machines or multiple devices rather than being done on a single machine or computer. So in simple terms, what we mean is that cloud is a powerful brain that conducts training, large storage, and many other things, while the edge is a local intelligence that is fast decision making near the user. So when you're talking about cloud and edge computing for distributed machine learning, we are talking about the brain under which it's working on large data sets and storage, and the local intelligence devices that make this data to be closer to the user or the consumers. I hope you are getting that. That's why here we are saying cloud and edge AI solutions for scalable distributed machine learning are very important, and they play that bigger role. The other thing that we need to know is that why should we have cloud and why should we have an edge needed in machine learning? So when you're talking about this, then we can categorize them into terms of latency or the problem that they solve, and you can be able to get what is the solution that we expect it to do. So latency, that is sending data to the cloud, takes time. That is in terms of the speed. The bandwidth, that means the amount that the machine model can be able to carry within a second or within a specified time, and the size of that data overload. The privacy, we're talking about the sensitivity of data that leaves the device, and the offline environments, that is some of the devices that have poor internet. Now, when talking about this cloud computing or edge computing now, because we are talking about these fast intelligence systems, what do they solve? So the problems that they are solving include things like the smartphone sensors you talk about. Instead of sending all raw data, you can maybe send some analyzed locally data that has been generated and so on. So we are going to look at all this and how it is able to operate. Because when you're talking about training and heavy processing of these cloud computing systems, we need to know what resources do they consume. The GPUs, the TPUs, the large storage and the distributed clusters. All this we have talked about them in the previous section. For example, you are working on a cloud train to develop the crop prediction model that uses the Spark or TensorFlow. So how do you improve the model in sent-back, edge, dynamics, and so on? So all these are very important things that we can be able to look at. But now, back to this, let's look at the cloud-based distributed training. How do you train these cloud-based systems? Um, we have Amazon Web Services SageMaker, which are the tools that we normally use in cloud-based distributed training. What do they do? They support our distributed training via the built-in frameworks like the TensorFlows and the PyTorch, which we are using as our model APIs to be able to configure that, and also the pipeline. The other thing that we would wish to talk about is they provide automatic model turning and elastic scaling, which are very, very important things to be done. And the other one is they are features that manage Jupyter notebooks. Remember, as we are using the Google Colab, they are linked with Jupyter Notebook Python, which works very well. They are also linked with the hyper parameters and optimization tools, and also the one-click deployment approach. So if you want to do that training and then deploy them directly, you can use the Amazon Web Services SageMakers. The second tool is Google AI platforms. That's why we are using the Google Colab, because it's a Google AI platform that has integrated all those. So you can be able to integrate Google AI platforms with the TensorFlow and JAX for large-scale machine learning models training. And that's what we did. You have always installed this to be able to use them. Then it offers the GPU and TPU values, because when you are using the Google Colab, it's completely consuming the Google Cloud space. That's why you could be able to access it through the Google console space. Because with the space now, it can be able to offer you high performance computing. And that's why when you're now accessing it, you can always be linking it with your Google Cloud or OneDrive to act as your storage point. Then it provides the auto machine learning tools for no coding model training, but you can be able to write some specifics that is needed. And the other one is that we have a third tool that is called the Azure Machine Learning. So the AML is also a very powerful tool that we use in addition to Amazon Web Services and Google AI platforms. So what benefits does the Azure Machine Learning give you? Because Azure will be given by Microsoft. AWS is given by Amazon, and Google AI platforms are given by Google. We have also those ones that are being offered by Oracle, which you can be able to get them, Oracle Cloud Space. The Azure Machine Learning supports the end-to-end machine lifecycle management. We also provide manage Kubernetes clusters for distributed trainings, which are working so powerfully with any machine learning models. So what are the advantages for us to use these cloud-based training tools? You need to know that they are powerful and they can help you to do a lot of things. One of them is scalability. They are very scalable and you can be able to change from one platform to another using the same model to be able to train. They are cost effective or efficiency, in that you can be able to only buy what you want to consume. You can leave the rest, but only buy what you want to consume, depending with your pocket size. And managed infrastructure, we also have managed infrastructure, which is much better. And it works because with the cloud computing space, the infrastructure is well and it's working 24 hours without shutting down. We talked about load balancing approach, and it's done in all the cloud computing space. So if one server is down, the other one picks up immediately and there's no issues with the consumption. Then we have the seamless integration with storage and data pipelines. This one works so well because you need to be able to consume all this. And then we have access to on-demand computing resources and serverless machine learning capabilities. And then we have edge AI for resource constrained environment. So what are these edge AIs that we need to use them for constraining this environment for our resources? Edge computing enables machine learning to inference, that is to close to data sources, making you move or making the system to move closer to the users or the consumers. The key concepts here is deploying AI models on the edge devices such as the AI, IoT sensors. We've talked about smartphones, embedded systems. We've talked about all these cameras. We've talked about any other tool that can support that. Smart tractors, industrial machines. All these are tools that can be able to work on because they are the first decision making nearer the user, and that's why we call them local intelligence. So edge servers and so on. Then we have reducing latency and bandwidth, which we have said that these are the things that it can be able to look at in terms of the processing of data locally. So what are the edge AI frameworks that we use? We have the TensorFlow Lite, which is optimized for mobile and embedded devices. That's why we need to train with it. And as we do the deployment today or training some few TensorFlow distributed machine learning, then we are going to use the TensorFlow Lite to be able to see how we can be able to optimize that to happen. OpenVINO, that is an Intel's toolkit for optimizing deep learning inferences at the edge. That is at the local intelligence devices. Then we have the NVIDIA Jetsons. So if you have been hearing about NVIDIA and so on, they are also picking because they are a platform for GPU as the acceleration, especially handling the graphical areas on AI at the edge. And then the edge TPU, which is the Google's hardware accelerators for on-device machine learning inferences. We also have challenges and solutions in edge AI. And when talking about challenges and solutions in edge AIs, we're talking about limited processing power using model quantization, the knowledge distillations, and pruning to reduce the computational loading. Then we have the energy constraints, which is optimize the models for lower power inferences and use the efficient hardware accelerators. We also have connectivity issues, which ensures some offline inference capabilities for deploying self-constrained models that have been built. Now, I want us to do this implementation so that you can be able to see. We are going to consume the same data sets that we have. That is the California housing data set. And we are going to see if we can be able to solve this or create this model and deploy this. The key thing that we are going to implement is deploying a distributed model to an edge device. And the objective of this practical is for us to deploy a trained model, machine learning model, to an edge device for the real-time inferences. What we are going to do is, number one, I want us to train a lightweight machine learning model using a TensorFlow or PyTorch. And number two, we are going to optimize this model using a quantization techniques to reduce the size and computation. Then we shall convert the model to format compatible with the edge device, because you must always convert it to work with the edge device that you are working with, such that it can be able to work with our edge device. What is the edge device that you have picked? We have picked our edge device as a TensorFlow Lite, which we have already said about them here. TensorFlow Lite. We can be able to do it with OpenVINO, NVIDIA, Jetson, and the Edge TPU. But today we shall use the TensorFlow Lite to be able to do our deployment. Then we shall be able to deploy the model to an edge device such as the Raspberry Pi, the NVIDIA Jetson Nano, or the mobile phone. And then we shall run the inference on the live data and measure performance in terms of latency, power consumptions, and accuracy. And then also we shall compare the latency and efficiency with the cloud-based inferences to evaluate the trade-offs. And then we shall end by integrating the real-time feedback mechanisms to improve the edge inference accuracy over time. That means that we are going to give back the system to the cloud edge to retrain it. So that is what we are going to do. Now, for us to have that practical, you can open your devices and then you can go to Google Colab. Then we can be able to start a new notebook. So you can come here to file, and then we can start a new notebook drive for us to be able to do that. So I want us to label it. So for us to name it, we can give it a name as Cloud Edge Computing for distributed machine learning. That one we are talking about the we are talking about the California housing datasets with Apache Spark deploying that. So we are talking about this architecture here. So we can just name it as we can have deploying models. So we can just say deploying California housing dataset model to edge device, or we can just give this. We can be able to leave it there. Now, the first step here is what I want us to do. And what you'll do there is that because already we have our data sets available within this area here. So it's just loading. Once it's loaded, then it can be able, we have our data sets here. That's the California housing data. So for us to do that, we need first of all to start with so what we are going to do is loading data using Spark distributed processing, training a model, converting it to the edge format, then deploy it with TensorFlow Lite, and then simulate inference on the Raspberry Pi or mobile or edge device. So the first thing that I want us to do is to install the dependencies. After installing the dependencies, then we are going to import the libraries into the space for us to consume that. And then after that, now we shall now be able now to start the session and then be able to implement that session in that area. So let's start by installing the the patch, the PyStat space, and then the tensor light which we need to be able to use. So we are going to install the PySpark TensorFlow and the TensorFlow Lite scikit-learn value into our model in that space. Then we are going to run that. So you can see here that it needs us to. So in case this is not picking, so it says requirements already satisfied. PySpark is in this. Could not find the version that satisfies the requirement TensorFlow Lite from the version none. So no matching distribution found for TensorFlow Lite. And we'll be able now to fix this. So we can be able to use uh, let's use any device here. We can even use Copilot to fix this, or we can use AI mode. Then I can say fix the error, and it's able to tell us. So meaning that it does not run this. So we need to install this so that it can be able to work with that. And then we shall also install this, the light RT, for it to work. And then now we shall now be able to use that by importing the TensorFlow interpreter to, to, to understand that the model in that area. So I think that is what we should be able to do. Number one, let us install the TF Lite within the space. So in case that is the error, we can be able to install that. Install that. Says that the version is not available. Then that means that we should be able to install our PySpark first. Then we shall be able to see if it can be able to pick those materials. So our PySpark is now installed. We can now be able now to test if now this one can be able to work in the second column here. So still it is refusing to install that. Let us repeat installing this. So this is the error. Can be able to ask it here, but then we can pick this. We can pick this and then be able to see if it can be able to work with it. Let's have the second code here. So this one has worked. So since we have now installed that, we can be able now to see if we can now install this environment. If it has refused now, this one is working with the AI age alert. Then we can now be able to see if this can be able to work. Come down here. Let us repeat that. The new model. So still it's not working. Let me see. Uh-huh. Let me ask it. Um, let's say fix the error with in Google Colab. So I think we should now use these two for it now to work. So we shall use these three before it works. So let's install this PySpark TensorFlow scikit-learn that. Uh, so let's see if this is going to pick. So it's telling us the environment is not so, but it says that it's already satisfied. So meaning that we can proceed with the rest. Let's look at this for it to consume now with Python for TensorFlow functionality. Let's add what is this thing? Yes. Allow me to restart this. Yes. So that is okay. Now, hope you can hear me there clearly. Now, once our engine has done all this, so it's trying to get some requirements to build a wheel. Since the package is higher, so still we can be able to use this with the notebook so that we can work with the local deployment. Okay. Now, since we have an error with that, but there is compatibility working, then we can still work on the other sections. So the other thing that we were saying that we need to import some libraries to be able to consume TensorFlow because we already installed the TensorFlow Lite and it picked. So we can be able to run that import to be able to import the TensorFlow as TF and be able to see if it can be able to pick and also if it can be able to show the time. So since it has worked correctly, we can be able now to run what is called, let's first of all put here text, delete this, I want to delete this, put here text. For this text, we want to edit. For this text, I want us to check what is called uh, step 2, which is Spark session distributed processing, because here we want to use to call this, which we have already activated and called, in order to check the builder of our app name, because we want to check the California housing to be able to start to load our data sets from it. So for us to do that, then we have to give here step 2. I'll be able to do that, make it bold and make it a title like that. I think that is okay. So we can be able now to start our step 2. And here we are going to be doing some loading and so on of that. So for us to do that, then we need to call the Spark X and call the builder because we are targeting our data. So what is the name of our app? We can call our app that we call it California Housing. And then we want to use this to deploy it. So we call the Spark session, which we have already activated here to come into session. And we have already imported it. We have also imported pandas, NumPy, to be able to help us work and the time for it to give us the timestamps. So once we have now called this our app into session and we have started it, we need now to load the data sets from the sources that we have. So do we have housing data sets? No, we are going to load our data set called we shall just name it because you already have this in your area. So I want us to load our data, and before that I want to add a text here. This is loading the data sets, select that, make it bold, so that now we are loading the data sets here. So which data sets are we loading? So I have to check here and now come here and pick this California training. So I can copy the path and then come here and load it here. So we are using that sample data there. So I'll run the code to check on that housing test CSVs. So it has already loaded our data. So the next thing that we are going to do is to display some raw fields that we need. That's what we just need 5 of them, and then display the schemas. So we are just going to add here text, displaying the first 5 rows of our data sets. And once it is like that, we can be able to make it bold. Then below it, we can be able to add, now that we are displaying the first 5. So the data is there. So once we have our 5 data sets that have been loaded, we can now do what is called check the schemas by printing them out. So we need to print out all our data that we have loaded into the schema that's available for us. So we need to come here and then check the schema. I hope I have not stopped that. All right. So let us check the schema here. Check the schema. Stock database. Like that. So let's check that and check our schemas. That is what we have. Now we need now to after checking our schemas, we need now to process this data. So we are going to step 3, whereby now we are doing data pre-processing by dropping the rows with the missing values and so on. So all that is now what we can do, so that we are cleaning and trimming this data to accept what we need. So we need to trim our data, get what is required, and then check the data sets using the header section for us to have it done, completely done. So we can be able to check that. Let's have, I'll delete this. Add, I hope this has not stopped. Okay. We have the device here misbehaving. I don't know why. Let's do our data here. So for us to do our data pre-processing using Spark, We are saying we are going to clean this data, dropping rows with missing values. So for us to trim this data, we can be able to say df, and then we are going to our data frame. Then we are going to do our data frame with the drop the any rows that are not uh, working for us. So once we do that, remember this is a function. So here is equal to, so equate it that, and we can be able to run it. And after that, now we need now to convert our data sets. Now let's now do with the conversion. Now here we need to convert Spark data frames with the convert our data frame with pandas for now machine learning to train very perfectly. Now for us to achieve this, we'll need to ensure that we use the function called the PDF or pandas for our data frame. Should be able to work on our data frame value to convert the values to pandas for it to be able to locate it and load it correctly. Then we can be able to check. After that, now we can be able to perform what is called checking the data sets if they meet the requirements or the level that we need. So we can be able to do the, can, I hope it has not stopped. Something is behaving. Let's do checking the data sets. Checking the data sets. So we are going to check the data sets using the pdf.head function. Then check our data sets. So our data sets can be loaded correctly. Now the next thing, after checking all our data sets, if they are available, converting the Spark data frames into what is needed, we now need to do the prepare the features and targets. For us now to prepare the features and the targets, we need to check all the areas that were dropped and then drop some values, target the variables sections and pick them, and then split our data sets into some small sections that we can be able to train and the ones that we can be able to test. That's now the XYZ. And next, we shall be able to look at the normalize features to normalize it and then bring them together. So what we are doing here is we are going to perform some to prepare some data there with that. So we can be able to have it here. And then from here now, we can be able to do that assessment uh, with with the entire process. Let me just share the entire code with you so that you can be able to work on it from your side too. Where have I saved it? I have given it here. And before that, allow me to so we can do the steps for preparing this. That is, we can start by preparing the feature and target before executing them, and then we split the data into segments for training and for target that we want to use. So you can code that first, then we can be able to proceed down. Code that step 4. Are you able to open the file? Or I see somebody sending something there. Hello? Someone has sent, oh, the password is, okay. Password is 1234567 8. Try use that. I think I encrypted it. Has it opened? Enoch. Fine. Yes, you can use that to do that. So you want to do the preparation of the features for that. For this case now, before we execute the entire area that we need. So first of all, let us find the target variables that we want to use to train that data. So first thing that we want to use the media housing value, which is the last column, as described or displayed here. Housing value, this last one, this last column, this last column here. This is what we want to use to do that. So with that, then we need to do that within the X and Y columns. And then, which I have not stopped that recording. Let me see here. Okay. Then we can easily now add a certain aspect here, which is splitting the data sets. Split the data sets for training and testing in 2 dimensions. So you can make it that way. So once we take that, splitting the data, so we need to split this data into the correct values and then assign the seed value. So for that case, then we need to load it using the uh, skit-learn model to select it and then train that data and split it into some percentage of 0.2% for testing, but training we are going to train it with 0.8%. So that's why we have this section here. So for us to split that, we are going to use the skit-learn for it to do. That's why it is playing a better role in that space there. So once you have this now, you have splitted our data so that 0.8 will be used for training, and for testing we are going to use 0.2. So we are going to run all this so that we can be able to split that data perfectly. And after splitting that data, we now need to normalize that data in order to ensure that we get the correct data to be able to scale it up and transform it to fit our training sections and our testing areas. So for us to do that, we need to apply normalization aspect. And for that case, then we need to use the normalization aspect, normalize the features. So we make it bold a bit. Uh, so we can proceed by writing its code. So the code for normalization is we want to train, you scatter the data into two. So you scatter the data, but we need to allow it to be processed through the standard scale that we need from that we have from our system. So we first of all we use the scikit-learn to pre-process this, and then once we have splitted it, then we need to import the standard scaler to be able to use it to scale our data into two areas: the training models, data sets, and the ones that is used for testing, so that we can be able to have the actual figures that can be utilized for that. After doing the scattering this and preparing these features as a target and getting the samples or the sizes that we need to train, and the ones that we need to test, now we can now be able now to use we can now start to apply the lightweight model in order now to consume the TensorFlow light to work on our model continuously, so that we can train the cloud environment collab values for us to have the solutions being done. So for us to do that now, we shall use the TF, that is the TensorFlow Lite that we needed to do. And we are going to use the keras layers to do that. And with the keras layers, we are going to activate, we said we shall be able to use the rake spares pi to be able to do that. So we are going to do that right now, and then compile that model to listen to all the sections or the metrics that we have, and then be able to now execute what we need. So for that case, we can be able to have uh, value here. So applying this in order to make the coding to be very easy to understand and learn. So let's do that. Let's split that and then be able to get our model working. So we are going to use the Keras sequential model aspect for us to take the input shape, train it, and then get the denser Keras values to be able to check that. So once we do this, we see here that it do not pass an input shape, dim arguments to the layer when using the sequential. Uh, Let me see if this. I think it's because our tensor light did not work. Let me see if it can be able to fix this. Model sequential this input 10 and input what? Let's say that assume this is the value. Let me ask it with this value. Correct this. We use this. So it has given this, but remove input X train shape, and it has added some values that can now be used. So the way it was before, it was consuming values that because if you look at what I have placed here, here it was not defining the exact values. So here we have to input those values, whether there are 10 values to be trained or what. So that's the correction that we have done here, and added the values to be explicit input layer for it to be able to work with that. So let's see if it can be able to work. You can just replace this model. So it has worked correctly. For it now to train that and get the reactivation of the missing point there. Then the next thing that now we shall be able to do is now to compile this and also train the model. So for us to compile the model, we need to compile the value that and call the metrics that we have used within the parameters to be able to get that done. So for here, we are going that now we are saying compiling the data and the model, the data model. So I'll be able to do that. Make it bold, and you can be able to do that here. Get that. So we are optimizing for Adam stand values and get the mean square error, and also now compute the metrics in the model assessment error detection. So for that case now, after we have done the compilation, we are now going now to train before we evaluate. So we need to train that model with certain values because we had picked 10 or batch size of 32, and we are splitting it to 0.1 validation value to be able to get then before we evaluate it using our X and Y value intervals. So let us train the model. Uh, so we are going to train the model using that. So it's consuming that and training that model. So you've given it to pick 10. Here, the number of columns here to be detected to be 10. So you can easily increase the value if you want. So it has trained in 10 column values. Then after doing that, now we can easily, I'll be still recording here. We can now do what is called the evaluation. We can now evaluate the tests that we have done, because we have tested how many models? 10, 10, 10 percent of that, and splitted that into that with a batch value of 32. So we need to evaluate that and see what is the results. So this one is evaluation of the model based on the trained size. Based on the trained size. So we can easily deal with that now, to be able to test that model now. So when we test this model, we can be able to detect that whether we are making a loss, because you need to get what is the loss, and then the what are we getting here. We were to test for this. Remember, up here we are to get the loss, mean square error, and get the matrix value. So that is what we have given. The loss is that value, and the matrix error is that value given to us. So after doing all that, training, evaluating, and testing our model, we can now be able now to do what is called now saving our model inside our space. So you've done all that. You need now to save that model to represent now the cloud model, machine learning model space. So we are going to save it as cloud housing model name, so that now we can now be able now to convert it using the TensorFlow Lite for it now to read. So we can do that by saving this model. So here is about saving the model. So we do that. So we were to save the model using its name. So we need to start with model save, and then you give the name that we want. So we can even give it any name that you wish. But for this case, since we are dealing with the housing model, cloud housing model, then we can be able to give it that way. I can rename it to California Cloud Housing Model. But this one is also just okay. So what does it say? That the model saved invalid file path extension for saving. Mhm. File path cloud housing model. We can give the name of our data set. What is the name of our data set? California housing. Can we be able to test with that? And then we see. Um, hmm, Model. Keras extension for the native Keras format recommended H5 extension. So what does it mean? Yeah, fixing this. Oh, it has saved it with Keras. I think that is what it needs to be. This model. Save for the further training. Keras use recommended this one, and then after that, for deployment now, we shall now do this, and then save in legacy format. We can now save this. So what are we doing? We are saving for deployment. We are saving to cloud model and also saving for deployment. So I'll do the two. So we shall do the first one with Keras. So we can do the Keras one, save it like that. And then we shall add the second one so that we can save it with the model name. So let's give it as California model with the cloud value there. So this can work. Now it has saved it. That is perfect to be exported for future with the Keras TensorFlow value. We can as well as save it with the third one, which it has recommended for us that now if we want, remember we have already saved it with the TF Lite for serving. Now we can save it also with the legacy format so that it can be able to specifically take the old HDF5 format also, so that all of them are available. We can do that, saving with the HDF5. You can be able to see here the warning is given, but it has saved. We recommend using, what do they say? They recommend using, instead of native Keras format, e.g. model save, model Keras, and so on. So still we have already saved using this one. And that one is okay. So our model now is saved as Cloud California. We can easily now look at converting this value. Remember the name that we have used. So we are going to convert this value using our current name that we have now used. So we have saved our model not as cloud housing model, but as our cloud California value. So we are going to save that in that space or in that sphere. So we can do the text here, and then we can save this to TensorFlow Lite. And when doing this, remember the name of our model up here. So we can easily use the name of our model, this one here. So this is what I want us to use. So we shall replace this on another code here that we are going to do. That is the one for optimization. So we are using this convert the model into the format that the edge can be able to work with. Because remember, we were to format it in the edge section so that it can be able to work as per that edge. And we say the edge is the intelligence target device that we wish to use. So here we are going to change the name to fit what we want. And for that case, we first of all, I can be able to put this one here and now come and change the name of the model to what we have here. Take this, can be able to change with that here. Yes. So we are going to call it housing age, which is okay. So we can run it. Now it's telling us that with statement on line 4, expected an indented block after with. Oh, what does it have? Let this one fix for me here because we need to have it a continuation here. What if I bring it here? Will it still work? Unless I separate them. So let me see. Yes, it has worked because this one a separation, there was no need for the block there to separate the fixing of the model with our TensorFlow Lite so that it can be able to work with it closely. So that one is okay. We have already converted that into now from the term called cloud housing model to what is called the housing edge model, because we say that we need to convert it to the edge model that can now be consumed by our device. Now we are going now to check if the model size is what is the model size for this. Now here we can say checking the model size. So you can easily do that. Make it the value, and then I can add a code down here to take care of that. So what was the name of the model? We need to change that name of the model to what we have. So our model is called Cloud California model. So change this cloud housing model to that California model that we are working with, because now our edge full file, TensorFlow Lite file, is here. And we want to check if the size is in kilobytes. And what is the size there? If it is, it must be, we take the value, then divide by 1024 in order to get the size of our model being consumed by the operating system that we are giving. So that is what we are doing here. So we are converting that, and we can be able to get that the size of our cloud model size was 43.3125, and now the size of our edge model size is now 6.7 7578125. So those are now the sizes of our model that we intend to deploy. So after checking the size of the model, you must be able to see the compression, which we have already seen that our value is giving. It has reduced from 43 point, from this value here, 43.3125 to 6.7578125, which is now a sizable section that we can now be able to deploy to our space. Now, having checked on that, we can now simulate the edge for deployment before we run the edge inferences for us now to check. So we need to do the simulation in order to load the model with the TensorFlow Lite, so that now we can be able to know what is the size and if it is ready for deployment to our edge section. So I can be able to do that, and then come back here, be able to add now the code down here for us now to do that, the simulation values. So when we are simulating, we are going to simulate our model with the name that we have given it, because we have already converted it into an edge understandable value that can now be deployed. So our new model part now is now called the housing edge model, which we have done the conversion here because we converted the name Cloud California Housing Model into our housing edge model that is now understood by the TensorFlow Lite. And now we have checked the size of our edges, and we have found that now all of them are saved because we did the saving, and we needed to check whether the saving was available. So I can be able first of all to make this one. I think I forgot to make it bold. So it is now okay. Uh, so we can be able now to check that, and then be able to execute that. So for our simulation, we need now to run our simulation here. So it's telling us that TF interpreter is deprecated and is scheduled for deletion. Let me see here what it is telling us. I want to get with the entire. So that is the interpretation, because we need to get that clear interpretation if it is working. Confirm this. Uh, Confirm the interpretation. And if it is true. So the warning indicates that Google is rebranding TensorFlow Lite as the Lite RT and starting with the TensorFlow 2.20, which will be removed. So to feature the proof, your code and remove the warning, you should use the new what is called the Lite RT library, which we should be able to install. But already we had installed this, and then update your code to the value that we need here. So I think since it's scheduled for deletion, we can still update it with our edge light value the way it is here, because now we don't want our value to be deleted in the near future. Simulate the edge deployment, load the model with TensorFlow, but we expected that as an error to come so that now we can be able to run the edge inferences. But before that, then let us first of all make sure that our model does not get deleted. Therefore, we can be able to update the model size here with the edge light that satisfies our current model size. Once it is done, we can now update our file using the import function here, so that it can be able to pick and then run that section now to do the interpretation. Use the light one now to interpret our value, so that now it can now interpret this value correctly for us to be sure of the value being used in the future. So this code here is just what we have had up here. So we want to output details and get that. So that is what we have now corrected. And for this, with this one now, we can be able to run because now it's consuming our new interpretation. So it's telling us that has not attribute interpreter that. Okay, so what we can just easily do is we can use the old version value here, but after we've done the importation with the current status here, let us do that and then run with that import. It will now work. So we can fix that with that. Now it has worked, and it is now working with our updated uh, light RT value without any error. We can now proceed to run the edge inference for us now to have our work being inferred before we compare the cloud edge and the inference edge that we have. So let us run the edge inference value and see what is the results that we shall be able to get. I'll do that and then run that, and then I'll be able to add here that code now to run that inference value. So the inference value has to look at the sample value that we have, compute the value for test and the float values, try to get the edge inferences value in terms of the time that it even did, the loss, the predictions, and the interpretation that were invoked so that we can be able to get. And we are testing the values from the first for all the 32 values that we had given it access to before we look at the comparisons. So we can be able to do that and then be able to run that. So right now the prediction is available, and we can easily tell from there that it has predicted our housing price to be 3,941 US dollars per that, 0.66, and the edge inference time that it has consumed is that. That is now the predictions as per the time interval that it has given us, because it has to check all the values based on the inferences that we have given it before for that model. Then after doing the inferencing, running the inference section, then we can easily now do what we need here called the comparisons to get our inferences based on the cloud and both the edge inferences section so that we can be able to get all the predictions that are available. So for the two, we can easily do first of all this test for this, so that now we can be able to do the test of the two to get the solution done, or to get our predictions as per the two, both the cloud and the edge inference, because we have done the edge inference here and we have already found the value. So can we be able to compare the two and find which one is achievable? So by doing that, you can now see our cloud prediction is at 940 and our cloud inference is 0.499, which means that within our edge, because the size of our value was compressed, you can be able to see that it was at 941, here it was at 940, and our time, how comes now that now our inference edge time is now shorter here compared to this one now? You see that? So that means that now for the cloud, it becomes it takes longer time compared to when we are testing it within the inference age, which is our faster. Because remember what we said here is that you need to ensure that with the TensorFlow, or when you are using the our latent values, it should be faster compared to what we have in cloud space, because we said that our when we are using our edge functions, they are faster compared to the one that when we use the cloud space there. If you remember in my first introduction, so we say that edge devices are faster compared to when they are deployed to the cloud space, in terms of because we were checking on some few things. One of them was the latency, bandwidth, the privacy, and the offline environment. And we say that the edge functions, which is the local intelligence, for faster decision making nearer the user compared to the powerful cloud, which is training large volumes. So if you have done that, then you are now testing what is now the size in terms of the time and the size that we have done within that space. So that is much clearer, and we have found what is the interpretations in that area. We've compared the cloud versus the edge inferences, and we've seen the values different. Now, in that case, now we have remained with just two tests to check. One of them is distributed machine learning feedback loop, and then we are going to check the latency benchmark now, so that now we can be able now to tell between the edge and the cloud which one is much faster compared to the other. But already here we already have the results based on what we see and the results that we have already obtained. So we can do that. Yeah, let's check that if it is possible in that particular values. Let's try to fix that, and now we can be able now to check the edge versus the cloud values if they are much better after the deployment and saving inside both within our edge deplorable section and our cloud deplorable section. So let's look at that dimensions. So we are taking a range of at 100, which we had tested. Remember, we had tested 10 previously here. So let's try to see if we can be able to take that. How comes it's giving us an error? Let me see what's the error. With the shape 1 to that. Let me do this. If I bring it here, will it still give me that error? View the problem. The problem is fixed, I think, because we need to call it with this area here other than making it to move on the other direction. So it's a continuation here. So we are checking for I, starting with the first area. So this is the if function loop. So we are looping within the range of our data within the at 100 data sets. We are checking from these data sets to check all the values of the amount that we tested, and then get within the float seed value, which was 32 value. Remember, this 32 value was within the training value that we were testing up here during training. Let's go to the training area here. You see here the batch size was 32. So that's what we are look checking and comparing with, so that we can be able to check that completely. Now for this, we are also checking the sample data in terms of the interpretations, how many has been invoked, and then be able to get the time that the age has used. And for the age, that is it. The same, we are going to do the same benchmarking with what? With the cloud area, to be able to get in terms of the predicted value of our model, and then be able to print out the average latency. And that we could as well as compute the other parameters, but that one you can be able to check. I want you to do that. A question on this area is that can you extend the latency benchmark edge cloud value to check the bandwidth, privacy, and offline environment? That is what I wanted to be done. So I can be able to ask uh, maybe the area here to be able to help me that while checking this, while checking this benchmarking, add other parameters like add other parameters in check in benchmarking benchmarking to this. That is, I want you to check bandwidth, the bandwidth. I want you also to check privacy, and so the third factor is that the parameter that I want it to be checked is offline environment, environment, environments, like that. So that is what we can be able to check. We can say update this on this. Let me say update this to check. Can proceed. I think so. Yeah, I'd post it. Hi. Okay. So can we be able to update this? I see if it can be able to add them. So it has said that it has to check this and print out all this. Okay. Let me tell it what it is now. That is, we are checking on we are checking on that is latency checking. So that is what we are checking, but still we can still consider this and see if it has the solution to that, because I can see it has given some full functionalities here that can check the parameter with the environment is the function, data remains on devices, and then the bandwidth and so on. So this one, all this is what I wanted to be checking. Let me see if it can be able to do that. Let's first of all check the first one here, then I'll check the second one. So average latency speed you can be able to see here, and average cloud latency. So the cloud latency is slower compared to what we have in the edge function, which confirms the results that in the edge function it has to be more faster. Now, what about now those other parameters? Let me put here what it has given me, because we are going to check the benchmark results as in this. Then check the edge as the cloud parameter, network traffic in terms of the bandwidth usage by the cloud and the edge. And then it's also going to check on the cloud in terms of the lower data transmission to external server, and data never leaves the devices in terms of the this. So we are checking that. And then we are also checking offline environment. Is it functional? So that no requires active connections, or yes, fully functional offline to be available. So let's try to see if it is going to give us the results on this test also. Let's be able to see that it's able to analyze that and give us the results. Perfect. Perfect. So it has been able to test for us all the parameters that we wanted to check in terms of the offline environments, the privacy, the bandwidth, and the latency. Why did we have to check for the latency? Because we were looking at the sending data to the cloud takes time. So you have proved that sending this data to cloud takes longer time compared to when we are using the edge latency. Number two, in terms of bandwidth, we have large data sets overload networks. So in cloud, you can see how much is it is 0.04 kilobyte requests, while in edge, the bandwidth is 0 kilobytes completely, meaning that it's faster here in the edge compared to the cloud. And the third parameter that we are looking at is the privacy. What we expect is to get the sensitive data leaves the device in cloud, but in edge it is not. So looking at the cloud, the sorry, in edge we expect the data to leave the device, while in cloud it, the data needs to be transmitted to the external server as a third party or a buffer in order to achieve what is called the load balancing that we were talking about. And then now for offline environments, some devices have poor internet, and therefore we have to look at so is it true? Because if you are talking about offline, some devices can be having some poor network. That means that some of the deployments will not take place to the devices, but it can take place to the cloud. So can we check that offline device here? It says no, it requires active connections, while in offline devices, you must connect it fully functional offline. So it has to work. And that's why we say that now when you're doing the deployment to the edge, you have more advantage compared to when you're doing the deployment to the cloud alone. Because for the cloud, you must have the internet connection, while in edge, you might have your sensors, your IoT devices, which have the ability to do this work, are offline, and they can easily be able to utilize your data and consume it. So I think that is the best that we have uh, that has worked with us, and we have seen all of them has been able to execute correctly and work with what we wanted. So I can just maybe just add maybe after this one, can just add a text here saying this is benchmarking to check. What did we do here? Let me just see here. This is to benchmark to check all these parameters. This all this, so that it becomes easier for you to understand the model in that sphere. So you can be able to do this, do that, and then do that. So that is what we had, and that is what within our model it can be able to have the explanations like that, for us to have that. Now the last part, now after doing the benchmarking, that we need now to complete by doing now distribution of this feedback to collect the incorrect predictions. So we can be able to do that very fast, and then load all our feedback and send back to the cloud, so that the cloud can now be able now to retrain the data, and then do or get the results at a lower state if it is consuming much of the spacing. So this is what we have. Can be able to get something here. So let us do this number, the last test, for us to end this. Hope my recording is on. So, okay, so it's working. So I can be able to do now the last, which is now checking all our feedback if they are correct in terms of our labels, in terms of our data. All that needs to be checked on. So we have to check that based on the predictions that we received compared to the model size that we have. So I'll be able to check that with all that to be able to get the feedback correctly and send the feedback to ours. So that now I can be able to explain that the steps that we have done within that architecture in the long last, in the long run. What do we have here? Oh, can be able just to edit this. Let me edit this code here. Uh, there's an error here. What is this? Let me delete this. I have to fix this. So for this one here, this is a continuous, so we can be able to give the prep here, and then do the test with this value from true or false. Does it require that true or false to come there? So that one is okay. Now for this one here, can be able to have this, and then be able to check if these are the data sets errors and large data sets threshold. Be able to check if our data has been predicted in that manner. Be able to get what is available for us. So I can just put this as an explanation, but it can have this data working closely together with this, so that we can be able to get the ABC pretense here. For us now to have this as can be able to put this one here. to explain that, to check the large error. So we are checking with which value. So we are getting the prediction with over 50,000 threshold values to be able to get the feedback for its data and collect it. So this is the value that we are going to do the prediction and find whether it is true or false, if it's working well within our model, because now our model has the ability to consume large data sets. So we are testing in terms of the data and the labels that are available for that. So after correcting this, I can now be able now to run, and it should now be able to work correctly and give me the predictions or the feedback, the correct predictions. So we are testing that to get incorrect feedback, and we can be able to get the incorrect feedback according to the sample collected is only one. But now, how can we be able to get the complete explanations for these predictions? Then I can be able to ask uh, this to explain the prediction results compared to what we have. I want it to explain to me the prediction results based on this. We can be able to talk with this. I want it to give the prediction, the explanations to the feedback on the below predictions. And what if larger range is used? What will be the expected results? What will be the expected results stroke output. So for that case, I can be able to give this so that it can be able to explain to me that, so that it can give us error by isolating this. So that is, you are filtering out the noise and focusing on the significant failures only. And the data curation here is that the feedback to be used is active learning instead of retraining to the entire data sets. So the edge to cloud cycle here is that in real distribution systems, the edge device identifies these errors, and only these specific samples are sent back to the cloud for retraining, saving, and bandwidth. So the expected results if the larger data sets is used is that now if you use like 500 or 1000 samples instead of 50, then it will happen. Statistical significance with only 50 samples, your feedback might be biased by fewer. But when you increase it, then the model will move to at least higher results. So I think this is the most important thing that you need to be able to have. So right here that update the feedback test with large models, with large model range, with large let me see here, with increased range, with large range for me now to test. So we can be able to have that to help us get that. So this is the updated one that it has given to us. I want to say that include explanations to be printed out in the model, so that we can be able to get the explanations being printed out in that model. That is much better now. This is now the much better results that I can be able to see because I'm getting the distributed interpretations, and that correct. This is now the best that you can be able to have. I'll be able to remove that the last part. So for this value, I'm going to add here more predictions, predictions and explanations on the range values. So we can be able to do this and get that done. Then we can be able to put here and then be able to, so this area here I don't need it, I don't need that. Can remove that. That is now okay. The error is gone. Can now run that prediction. Now what results do we get? We have now gotten that starting distributed feedback analysis range with 500. Analysis complete, samples analyzed 500, representing a broad slice of the California market. The error detected is 491 instance where the model missed by the 50,000 values. Failure rate is 98%, 0.20, and the distributed machine models here status is high error rate, and the explanation model is struggling with global generalization. This large batch of feedback data is critical for training. So actions collected is 491. Hard examples for the cloud training queue is now given out. And that is what we wanted, that after getting that there are some errors that it receives, what should it do? It should be able to send back to the cloud for retraining. And we wanted to get what are the explanations for retraining or for that sample data to be retrained. According to what we have first on the sample size that we have tested, the truth was that we only had one sample here to be resubmitted for training. But you see now, after I have extended the large data sets, because we were testing 50. So in the range value of 50 here, you see the value was one error only. What if we updated to 100 or 1,000? Let's see that. How many errors will be retrieved also for that area in terms of the feedback? We expect the errors to be, the amount of values to be retrained should be higher. It should be so large. Mhm. It's taking longer. It's still executing. Well, what about 10,000 values? Because it's checking with that pre-values of around dollars, $50,000. Do you have the $50,000? So it has refused that because the model was not tested with that value. So the time bound that it has been given here is too little and too short. So we can be able to shorten this to around 100. 100 can be able now to work at least. This one want to be able to take that longer time compared to the 50. Let me see if it is able to execute that. Perfect. So it has returned with the feedback of 1. But now you see, when you are now adding more explanation to that and then testing the value up to the range of 500, then and checking our threshold error of 50,000, then we have got this results as the output here. Mm. So the errors are too much, and they form the basis for our model to be retrained back. So I think that is the what we wanted us to look at and be able to get. So the final architecture that you have built is you've used the Spark distributed training models with Apache Spark. You have trained using the TensorFlow model. You have done the model optimization, removing all the errors that were there, cleaning the data into a very complete header. Then you have used the TensorFlow Lite model to be able to get the frequency and the latency feedback based on the, or to do the benchmarking, both with the edge device, that is the Raspberry Pi, IoT and phone, and also the real-time predictions using now the cloud space. And then you have been able to get the feedback data, and you have been able to give an advice back to the model to be able to retrain the model so that it can be able to get the best results that is required. And I think that makes the end of our session in that particular area. I don't know if I can be able to share the model with you so that you can as well as build on yourself. Uh, Let me remove the restrictions so that you can be able to access that model. Uh-huh. So the model is available now. I can be able to share with you guys to be able to check on that, and also be able to test with now with your level of retraining. I've sent it in the chat section. Please, you can access that model in that area. You can as well as check with other parameters, additional parameters, and then be able also to use it maybe to solve some other problems such as smart farming sensors. You can maybe get some data also from the smart sensing data and so on. You can as well as use to train those other sample data models that you have there to be able to have the best results on your end. Uh, that has been an intensive engagement on that sphere and that space. I think I've given you guys the password, so use that to access that model on that area. Yeah, access the model there. Access my model here. I build model here and modify to fit your desire. Please, once you get it, create a duplicate of it. Do not modify that model, but create a copy of it so that you can, if you want to do some changes, you can do the changes on that duplicate model. Kindly, that will be able to serve best. Yeah. Yes. So let me read the attendance section for us to end the session. Uh-huh. Let me first of all pause to see, to be able now to see that now my guys understands now how machine models or machine learning now works. Because the front end now, just like chat GPT, what you are interacting with is now the front end, but the back end is now where you have the models like the ones that we are building now. So that is what you need to know. So when you see the chat GPT, the front end, you don't expect that that is how it is. The back end is where we have the models. We have the models that are of different versions linked to the front end now. Now, when you are just logging in and now have the chat section there, just know that you are interacting now with those models which have already been built, like the ones that now we are building here. So that is how you do it, and you can be able to train your model anytime. You can update your model anytime. You see, now once I have it now accessible, I can now be able now to modify it the way I want, so that now when the front end now is now interacting with that, that person is able now to get that correctly. It has been a long uh, lecture. I didn't expect it to be that long. Diana Jerusha Olulo, is Diana available? Can you hear me? Or people are not?
Yes, I can.
Diana, you are there?
Yes.
Joseph,
Present.
Rolo Serena,
Present.
Mwashuke, Mjomba, Ondieki Enoch. Enoch, are you there? Isaiah, David, please mention faster so that I can move. Isaiah is absent. Austin Kwalia,
Present.
Njogu,
Present.
Bong, Lawrence, Enoch, Ikavi,
Present.
Norbert Muma, Ondiek, Shepkoech Joy, Kariuki Carol. Is that Kariuki? I haven't heard the name. Ochieng Victor, Mogeni James,
Present.
Nyet Emmanuel Ngugi,
Present.
Masibo Joseph, Gitonga Teddy, Mutwiri Maxwell, Machuki Regan,
Present.
Oyaro Collins, Ondiek, George Mudama,
Present.
Odhiambo Mike Jeff, Mwikali Brenda Kavata,
Present.
Kitavi Sharon,
Present.
Kibet Abigail, Gichuki Mwangi,
Present. Kibet Abigail.
Sandra Munyiva,
Present.
Cindy Michelle,
Present.
Kevin Kiplagat, John Maina, Susan Mohammed,
Present.
Walubengo Samson,
Present.
Gloria Wanjiku, um, Wanjiku Munge,
Present.
Ian Tech,
Present.
Julius,
Present.
Damaris, Wangari, Damaris is absent. Okay. Then Mwera Wanjiru,
Present.
Wakungu Wekulo. Fine. Let's meet next week to finalize with anything that might have remained. For now, I know that we are almost done with that. Today is 10th March 2026. So I might finish with that syllabus next week, so that you do the presentation of your project. Class rep, you'll remind me when is that presentation. I said 1 week to the exam. So, oh, no, you have to do it earlier because I have 4 projects to be presented, so by different classes. So you let me know if people are done by next week with their projects and they have linked with the front end, then we can be able to proceed and do the presentation. Uh-huh. So thank you so much. I think I have come to the end of this session. Unless you have a question, you can interact with the model and do other additions. Goodbye. See you next time.